So, good morning, everybody. So today we now start the second day of the med school. I'm very happy that we have together Valerio Beni, Dr. Valerio Beni from RISE Institute in Sweden. Thank you very much, Valerio, for accepting the invitation.
You're welcome.
Let me say a few words about the webinar and Valerio. So, Dr. Beni will speak about screen and inject printing technologies on sustainable substrates. He will make an overview on hybrid printed electronics and enabling technology for sustainable electronics, and on how material selection development can influence the sustainability of electronics. So a few words about Dr. Beni. He received his degree in chemistry from the University of Firenze in Italy in 1999, and a PhD degree in chemistry in 2005 from University College Cork in Ireland, following postdoctoral experiences at the Tyndall in Ireland, and later in University Rovira Virgili in Spain, an academic period at the Linköping University in Sweden. He then joined in 2015 the RISE Institute in Sweden, where he is a senior scientist and a project manager with core interest in the area of hybrid printed electronics and their application to manufacturing of sustainable electronics. So we're very happy, Dr. Beni, that you are with us. The floor now is yours, so please go ahead.
Okay, perfect. Thank you very much. And that's very, very important for me to talk to younger scientists or scientists that they are just approaching this field, because I think it's a very exciting field in the upcoming years. A quick outline of the presentations. I will give few slides to introduce RISE, in case you don't know RISE, and the printed electronic arena, so my facilities. A short overview, introduction to the printed electronics and hybrid printed electronics. Then I will follow up with some stories from RISE, so to show you how this technology could be used in manufacturing of sensors, electronics, and so on. And I will close with some of our vision and effort on sustainable electronics, also how we can use hybrid printed electronics to make more sustainable electronics. What is RISE? RISE is it's stand for Research Institutes of Sweden, and it is a large compendium of laboratories. We have around 130 laboratories, and we have around 3,500 people. So just to put in perspective, internationally, it's equivalent to what could be a Fraunhofer, could be a CNRS, and so on. And we span from a variety of areas that goes from materials to electronics, data, AI, and so on and so forth. I am based in Norrköping, in the so-called printed electronic arena. That is a national effort to bring printed electronics into the industrial landscape of Sweden. And this is already giving you a little bit of an idea of what is our focus when it comes to printed electronics. We do have fully equipped laboratories for manufacturing, for electronics, using a variety of technology, and the core technology we are looking at is screen printing and inkjet printing. So the selection of the two of them has been mainly done because these are more mature technology, they are more scalable technology, and can allow actually to have a transition between research laboratories and industry. We also have a fully equipped labs for characterization, and we also do some chemistry. So we have labs for the chemical development of inks and materials. And you will see a bit of it at the end of these presentations. Among the different areas that we are looking at, we look at green electronics. That's so, or synonymous with the sustainable electronics. We look at different ways of producing and printed electronics. We look at medtech, health, packaging, sensors, and energy storage. But what is printed electronics? I'm not sure if all of you are familiar with it, with this one. But what is printed electronics is this the technological field that use additive process. That could be in this case we mean printing and dispensing for the manufacturing of electronic circuits, sensor, electronic device on a variety of substrates. And what we actually mean is we add materials on a substrate. That could be a foil, could be a more rigid substrates in a liquid form. We will look into this one a bit later on. That is actually called inks. We make them solid, and then we deposit a second layer. So basically, we built up a system and device on a layer by layer approach, so step by step approach. And I will give you a very quick introduction of some of the technology used to print materials, some of the requirement of the materials, but also some description of what is the curing process and so on. To make printing and to make printed electronics, we just need two main elements. We need materials and we need the deposition technology, the deposition tools. And printing, what we use, print electronics, is to make, as I said, electronics, but that's exactly the same technology that you use to print, or derived technology to print newspaper, or to print, for example, T-shirts, or in this case, bags and other gadgets. There is a compendium, very large compendium of printing technology. I believe that during this series of seminars, you will actually encounter a variety of them. But if you look at the taxonomy, so how you define them and how you identify them, you can divide them basically in two main families. One are process having a physical masters. And in this case, it includes, for example, screen printing. But you also have a printing process without a physical masters, or they can be called also a digital printing. And that's where inkjet printing fall in. When you move from one technology to another, of course, you will have different performance, you will have different requirements and different limitations. As you can see here, this is a very busy tables, but the message that I want that you take in consideration is that when you go from screen printing to inkjet printing, you will have significant, you will have requirements when it comes to inks, viscosity and surface tension, quite high difference between the two of them. The two processes provide also completely different resolution. For example, you can go very in inkjet printing, you can go few microns, tens of microns in terms of resolution, while screen printing with more conventional technology, you go in the order of hundreds microns. And another element that is very important is the throughput. So how fast area you can actually manufacture using this different technology. That's actually very relevant when it comes to the industrialization of the process. But let's have a quick snapshots to the actual two technology that I want to introduce to you. So this is screen printing and inkjet printing, aerosol jet printing. So screen printing, let me see, I should have a video. Let me see if I can manage to make it run. Yeah, so screen printing, as I said, it's based on let me see if I can find the pointer. Can you see my pointer? No.
No.
Now you should be able to see.
Yes, now we can see.
Okay. So as I said, screen printing, it's follow in the categories of the manufacturing process using a physical templates. And the physical template is, if you look at the video, it is this pattern on this pink, now it's pink, structure. So you predefine a structure onto a textile frame or textile foil, on which you actually create some voids where the inks is then pushed through using blades. What is the advantage of screen printing? Screen printing is a very quick technology, so you can actually manufacture relatively large areas at a relatively high speed. What is the main drawback of this technology is that this technology since it requires a physical templates, it actually have is not very ideal for exploratory works. So you are actually bound to what you have on the physical screens. But this is one of the technology that have been mostly implemented in the early stage of device manufacturing. For example, glucose sensors have been developed. The first glucose sensor, I guess you have been coming across them, have been manufactured by this technology on very large scales. And I think while non-contact printing or digital printing are technology that's a built-up structure by depositing drops only in required areas. And there are different ways of dispensing it, but basically what you get a reservoir, you get a nozzles or a nozzle or a dispenser where the inks it's pushed through using, for example, piezoelectric forces, and this is only dispensed onto a carrier that is called substrate where it is needed. This is a relatively slow process, but allow you to get relatively good features in terms of width. As you can see in the image over here, inkjet printing is quite tricky to be implemented in terms of you need to really optimize the process, and you really need to optimize the material in order to get a very good lines. The one that I'm showing at the moment, I hope you can still see my cursors. It's the target structure that we want, for example. But if you actually have too much separation between the droplets, you will have the droplets individually, so you will not create a line. This line start to build up when you actually overlap more the droplets. But if you overlap the droplets a bit too much, or if the wetting properties of the inks are not adequate, you will actually have a spreading of that. So it's not a straightforward technology, and it requires some optimizations. A similar technology that is actually becoming more and more interesting, more and more attractive, it's so-called aerosol jet printing. Aerosol jet printing, it is similar. It's use a stream of gas to bring on and to move the droplet, to generate the droplets. One of the advantage of aerosol jet printing compared with the jet printing, actually are two. The main advantage is that aerosol jet printing is more independent from the viscosity of the inks than inkjet printing. So in the case of inkjet printing, you really need to tune very well the viscosity, while you have a little bit more of tolerance with this aerosol jet printing. Another very interesting and important features of aerosol jet printing is aerosol jet printing allow you to build structure or to follow 3D structure patterns. So you will be able to print on substrate. They are not fully flat, and that will allow you to look into more conformable electronics, or electronic that follow the shape of the surface, but has been originally developed, for example, for using interconnection of chips, so of bare die electronic chips. So you could actually use this one to contact the different parts on the chips, despite the fact that these are not flat compared with the original carrier. And I will show you quite a few results on the when it comes to screen printing, but I just want to give you a little bit of an idea of what could be done with inkjet printing. So you can print different materials. You can create, in this case, you can print OLEDs. You can print 3D structures. You can print or dispense droplets on a very precise way. And I will show you an application that we developed together in a European project with one of my students later on. You can print energy harvester, circuits, energy storage. So you can do quite a lot of activities, and I believe that Costas, in your lab, you actually have quite a lot of expertise and device manufacturing on this one. So I think Mike comes in other talk as well, a bit more on this one. Now that I gave you a quick overview of the technology that we can be used for doing the printed electronic manufacturing, I would really like you to move towards the second key or pillar of printed electronic, that is the materials. I'm not sure how familiar you are with materials, but fundamentally, to develop electronics, you need three main families: conductors, insulator, and semiconductors. And these materials can be combined in a different way to create a different device and different systems. Of course, as I mentioned to you, additive manufacturing, printed electronics require this material to be in the form of liquid dispensable solutions. So how you do this, or what you do this one? So what you do, you need to bring the materials into so-called inks. And in a typical ink, so you have different components, different components. Of course, the two main components are the active material and the solvent system. Where for active material, it's actually the dried what's provided to the dried printed inks, the desired properties and the desired functionality. And this could be, for example, metallic particles, in case you want to build, or metallic nanowires or metallic flakes, in case you want to build conductors. It could be a polymer, and the polymer could be a semiconductor polymer. It could be a completely insulating polymers. And it could be a pigment, in case you want to make graphical graphical prints and so on. Of course, as I said, this material need to be in a liquid form, so they need to be soluble or suspendable into a solvent or a mixture of solvent system. Not only, we need these two materials often they're not enough to create a very good inks. As I said, the performance of some of the manufacturing technology are strongly dependent on how the inks interact, for example, with the surface. How are the how do you say, the viscosity properties, how is their surface tension. So in solvents, you will have a series of additives. And these additives could be surfactant, for example, and these are used to tune the wettability. There could be thickeners, so to modify the rheology, the rheological property of the inks, and are also stabilizer in order to ensure the stability of the inks itself. And finally, but not last in terms of importance, the actual binders. Binder, it's to ensure that the developed inks after drying stays on the surface. I think you yourself could. This is easy to empirically understand. If you have a suspension of water and some particle could be sand, when you put on a surface, they stick nicely together when they are wet, but when you dry out, they actually become very dusty and they can fall off very easily. So you need a system that's called binder that keep them in place when the ink is actually dry. Of course, what do you need to consider and optimize when you make an inks? As I said, you need to consider the solubility or dispersibility of the different materials in the solvent. You need to also understand the nature of the solvent. For example, his boiling point, his hydrophilic and hydrophobic nature, and this will influence a lot how the printing process takes place, how this absorb and works on the surface on the surface where you manufacture. And of course, you need to look into the properties, for example, the wetting, so how these interact with the surface where you print, because depending on how these interact with the surface where you print, you will have a different way of the inks to spread and to create structure. Just to give you a very quick, a very simple example, if you take a baking paper and you put a drop of water, the water will actually sit on top of the baking paper quite nicely as a drop, so will not really spread on it. If you put a drop of water on normal paper, this will actually get absorbed very quickly and disperse very quickly. And then in this way, you can think how interaction between the nature of the inks and the substrate can affect in general the printing process and the manufacturing process. Of course, as I mentioned before, a very key aspect is the rheology. The rheology it's very important to be able to use a paste on for the different technologies. So there is a very relatively narrow windows of rheological viscosity that could be used for the different manufacturing process. One aspect that I didn't mention, and I apologize for this one, especially when it comes to inkjet printing and aerosol jet printing, you have limitation in terms of the physical size of the particles, when we talk about particles present in the inks. So usually you need to be of the order of few hundreds nanometers. Otherwise, you will have a high chance or risk to clog, so basically block the nozzle or block the output of the inks. So these are all aspects that need to be considered into the manufacturing of inks. One last steps that I'm going to quickly mention to you is that, of course, I show you two of the technology that we use on a daily basis, or two or three of the technology we use on the daily basis for the manufacturing electronics. I gave you an extremely brief and very bird-eye view on the materials and material requirement and what you need to consider for the material. But there is the last steps that is actually also very important. That is actually the curing. And the curing, it's the way of solidifying the inks onto the surface. There you have a variety of curing process. This is the most common one, but there are also a lot of other curing processes that they are under development or they are more on exploratory. The most common is the thermal curing, where you actually simply evaporate and dry out the solvent and dry out the inks. You have UV curing, where this is mainly used for dielectric materials, where you use UV light to cross-link monomers or molecules inside the inks so that you actually create a nice and uniform films. But some of the inks require curing at higher temperatures in order to increase their properties, especially when we talk about electrical properties. And this could be infrared or near infrared or photonic treatment. So these are all treatments that use high energy light to heat it up locally, the inks, in order to increase their properties. Before we move to some concrete example or some more fun of this talk, I just want to look into very quick recap slides, or where I want to really point it out when to use printing electronics, or when printing is become a valuable technology in our view, and some of the issue that could become from with printing electronics. So print electronics, it's very important when you go in high volume production, when you actually look into large area device, so where you are not looking into very small features. It's very good when you look into flexible substrates, so like plastic foil, papers, and so on and so forth. When you look into cost-effective device, where you have a moderate requirement on size, so not too small features. Of course, the features you can do with print electronics, they're not really comparable with the sub-micron features that you can easily do with a standard, for example, photolithography process. And moderate requirement in terms of complexity, and I will show you later on why. Some issues with printed electronics, of course, the intrinsic characteristic of printed or the printed layer can be a limitation. For example, the thickness and the lateral resolution in the manufacturing of high performance device. And this, for example, it's quite relevant in the case of transistors. Inhomogeneity of the materials and the variability in the process can actually affect the yield. So you might create not uniformly reproducible device on a larger area, or you could have defects. Since this is a layer by layer process, registration between the different layers is actually very important. It could affect the yield, and this could be affected by the process in itself, but also by the material. For example, material that have they can shrink or swell as a function of, for example, heat treatment, could bring some issues in this regards. Printing and curing might suffer from printing and curing inks might suffer from electrical instability. Could be thermally unstable. Could be UV unstable. For example, some of the semiconductive polymers are sensitive to UV light. Can be mechanical, for example, can be brittle or poor adhesions, but also can be sensitive to chemistry, for example, humidity, oxygen, and so on and so forth. And of course, the substrate can be sensitive to thermal treatment. And very importantly, silicon components are commercially available in package form. And this is go back to the hybrid print electronics that we'll introduce in a few slides. In terms of hybrid print, when we look into hybrid printed electronics and when we want to combine silicon components with the printed electronics, it's still challenging since the most available components are specifically designed to meet the traditional PCB electronics requirement. Let's move on to a bit more fun. I think we'll need another 20 minutes. Is it okay, Costas? Then we got leave around 10 minutes for question.
Yeah, no problem. Yes.
So I just give you some example on printed electronics and success stories at RISE or what we are doing at RISE. I will focus quite a lot on screen printing, and I will focus quite a lot on sensors, since sensor, it is when I started at RISE was my passion, and it's still one of my passions, together with sustainable electronics. I think probably some of you, or probably you could easily find on the web, there are a variety of companies and there are a variety of provider of sensor that actually are printed. Physical sensors where you can look into moisture, you can look into temperature, you can look into strain, you can pressure, and so on and so forth. And as quite few other players, we also have ourselves, we have developed what we call the so-called sensor kits. So it's a variety of a physical sensor that we have developed, and we use with our collaborators and customers to actually get used to understand what is printed electronics, or what printed electronics could bring to their business as a first landing spot. And we have manufactured them on a variety of substrate, plastic, paper, and so on. But we have been looking quite a lot into printed electronics for sensing, and on more fundamental studies. One area where we have been quite active recently, and we are getting more and more active, is the organic electrochemical transistors. I don't think we have neither the time to go in, and I don't have the knowledge to explain you in detail what an organic electrochemical transistor is, but it's basically a three-terminal system that is characterized by extremely high amplification capability, and have been widely explored into microelectronics. What we're doing here, we use this high capability of amplifying signal to generate biosensors. This is a collaborative activity within RISE and the Linköping University and the University of Modena, under the umbrella of a Borges ITN project, so PhD training process. And what we developed by chemically modifying one of the terminals of these transistors, we managed to develop uric acid sensor that is applicable to the wound care monitoring. As I said, that this kind of device do not only have a very good, they are characterized a very good amplification process. And what we looked at was how can we use such a kind of transistor to amplify and to and to pick up very small vital signal. What we developed with a PhD students at Rice, we combined this printed transistor with printed piezoelectric sensors. Not sure if you are familiar with piezoelectric sensors, but just to give you a very quick indication, is a piezoelectric material is a material that will generate a voltage when it is mechanically stimulated. So if you bend, if you hit, or you will record a voltage. And this is what we do in here. We actually managed to develop a process for manufacturing sensors onto a tattoo paper. Tattoo paper is what you find, for example, it's a transfer paper materials that could be transferred onto your skin for temporary tattoo. And this was very popular back in my time for having when I was a kid, to have this. You could find in the newspaper shops this little tattoo, and you could put it on your skin, and it would stay for a few days and so on. But what we did in here, we manufactured these sensors, and we coupled them with this transistor to actually amplify significantly the signal. One thing I really wanted to give a very quick hint to you is this one. I think it's a very interesting result. Is that, as I mentioned to you, by changing the technology, you can change the size, the critical size of what you print. And what you see in this small graph is that when you go from a screen printing red line to inkjet printing blue line, manufacturing of the same part of the transistors, you have a much faster and much higher amplification response. And that's one of the interesting things. So by combining different technology, you could actually tune the performance of your sensor, of your device. In this case, it's a sensor, but you can do the same with electronic printed electronic device. Just to move on, as I said, you can also use inkjet printing, not only to you can use inkjet printing or aerosol printing to actually precisely dispense materials. And what we did in here, we use this digital printing to dispense hydrophilic materials onto an hydrophobic substrate in a very well-defined areas. And what we generate some sort of stop and go valves on a 3D printed microfluidic device. And what is very interesting is this process it's a permanent process, while conventional process for activating this sort of device, they are temporary. So, for example, you can change the hydrophilicity by photonics treatment, but this is go back to it's only temporary. But these are just components that we can build. But if we move a bit forward, how to increase the complexity and the complexity of the system that we developed, and I will show you a quick example of it. It's by so-called hybrid printed electronics. So hybrid printed electronics is basically to integrate and take advantage of printed electronics, so flexibility, conformability, with the advantage of conventional silicon components. Just to give you an example, you see this, I would say this microchip. This microchip is a tiny silicon component, but if you want to have the same functionalities by printing, you will need to print more or less a soccer field in terms of area. So you can understand yourself what is the advantage of integrating the two things together. Another advantage that I like a lot this picture is that by hybrid printed electronics, this is an example of it. You could actually integrate very easily electronics into textile and similar. While in the early case, this 2015, so it's in technology area, it's a long 10 years, a really long way back. But you know, this was one example of wearable sensors. But you see, the sensor can be actually manufactured directly on this, add on the skin using this tattoo system. But the electronics, it's actually still a bulky electronic system that could be put on your wrist. But if you consider that this one could be replaced by such a kind of system, you can actually understand how easier and how more conformable everything could be. I want to give you two slides that they jump by themselves, sorry. So this is, it will jump back, but you see, it is a very crowded slides with a lot of different functionalities. To obtain this functionality in 2014, we required 1, 2, 3 chips. While the interest in hybrid printed electronics it's getting so strong in the silicon industry that's right now, this is a 2018 example, all the functionalities, I think as you can see my cursor, the same functionality right now, they are actually all integrated or could be integrated in a single chip. So there is a strong interest from the silicon industry to integrate their own materials and their own chips into such a kind of a single-use device or printer electronics or hybrid printer electronics device. This is also a very good transition step because this was one of the first complex systems we actually developed on paper with the aim in 2018 to look into sustainability. So this was a starting point for us, and from that one we start to actually develop a full line of research on sustainable printed electronics. And this is the last few slides that I want to give you as an idea. What is sustainability? I will not go in any detail. I think as far as looking at the program, there will be at least 2 talks on this one. So I would just give you a very quick snapshot. So sustainability is the ability to maintain at a certain rate of level a certain process. And sustainability we can look at environmental sustainability, we can look into economical sustainability, we can look into social sustainability of the process. And I will not go into detail of this one. One thing I just want to give you, raise your interest that please follow the lecture on life cycle assessment, because it's a very good way for you to understand which tools could be used and what is meant by sustainability in manufacturing of products and electronics, and in this case, printed electronics. But in our view, what we need to do and what we should do to have a more sustainable electronics is actually to rethink our economy toward a more sustainable society. And I give you just a few examples of how this could be done. They are just keywords, but they make you think a bit. You can actually do action in the take area. So this is a typical production economy where you go from take. So you take resources, you make a product, you distribute the products, you use the products, and then you dispose of the products. So you finish the product. When you go into take, you can actually, why we don't use recycled materials instead of raw materials? So can we reuse materials coming from other device, other process to actually make new process? Can we actually replace the material, going from scarce materials? So that scarce material are material that are not available on an infinite amount and replace them with more abundant materials, one metal with another metal, for example. Can we actually use renewable energy instead of fossil-based energy? Can move from resource-hungry process in terms of energy, materials, and so on, to resource-efficient process, for example, printing. Can we actually expand the lifetime of a product, or can we actually make the product repairable, for example, instead of being single-use? One example is your mobile phone. Modern mobile phone, old mobile phone, you could replace the battery. Modern mobile phone, it's almost impossible or economically not viable to replace batteries, and you discard everything. So can you actually go back to the replacing the components if they are damaged and keep using the same device? And of course, end of life. Can you actually recycle materials and recycle components instead of just discarding them and in landfill or incinerating them and so on and so on? And how can we do it? We think we can actually act on a variety of levels. We could change the substrate, the material on which we print, so we can have a more sustainable material, recycled plastic, wood, paper, and so on. Can we actually change the interconnection material? So can we use alternative materials, metals, instead of the traditional metals, they are silver and copper, to produce the interconnection? And one thing we are doing is, can we actually use alternative way of generating and storing energy instead of using traditional batteries? When we look into alternative boards materials, for example, we are looking quite a lot into paper and paper composites to create a new substrate on which we can actually print and manufacturing the materials. We are at RISE looking at the moment in a European funded project looking at wood. So can we actually use wood as a replacement of plastic or more rigid substrate to actually produce printed electronics and electronics in general? And might sound a bit naive, but there are also business going around it. So this Jiva Materials is actually developing a press board that could be actually destroyed into hot water. So you actually melt down, you recover the components, and you recover the constituent materials. As I said, can we actually replace some of the inks that we use for manufacturing print electronics that is based mainly on silver and copper, that they are not only expensive, but they are also a scarce material, and they have a quite significant impact on the environment with other materials. And we are looking into, for example, developing zinc-based inks, or nickel-based inks. So low, more abundant material and less environmentally impacting material, to see if we can actually create electronic components with less environmental impact. Of course, some of this material, beside the environmental aspect, we also look into the performance in terms of conductivity, in terms of environmental stability, and so on and so forth. And that's where is the challenge. The challenge is not only to make an inks using a different material, but is actually having an inks that has a value in terms of performance. And we could look into IoT components on wood or paper, for example. And we have been developing electrochromic display. So there are display that show they can show a message by having a conductive polymer that change color upon electrical stimulation. We can do it we did in paper. We could build the sensor, as I've said before, of this sensor kit on paper substrate. We can make complex electronics device on paper substrates. This is another example of what we did in the ScreenSense project. Or you can actually directly print or engrave or manufacture sensors, in this case a moisture sensor, onto the substrate, in this case wood. And this is my last slides in terms of and then there is a couple of knowledge slides. Of course, one thing we are looking heavily into a national project is that it's almost a 10 years long-lasting activities that can we actually bring a forest-based materials. In this case, it's cellulose or cellulose derivatives and process based on the paper industry to actually make electronics and electronic components. And what we have been looking quite heavily is to create batteries, actually batteries and energy supercapacitor. So here, what you see here is it's basically a roll of a material that is based on cellulose and carbons. That it's using a conventional paper machine, so you can actually make a long roll of it, and that is used into the production of supercapacitor cells, where supercapacitor cells are kind of low, low demands energy storage for short terms, and usually very nicely coupled with energy harvesting. And what we have been looking also, we have been looking at using cellulose and different cellulose, modified cellulose materials to make energy harvesters based on triboelectric phenomena. So basically using at polarization charge when materials are different with different properties get in contact. Of course, this is the needed acknowledgement slides. You cannot do a lot of these activities. These are all public activities, and you cannot do a lot of these activities without proper funding. And our main source of funding for this the project I've been showing, the results I've been showing you, are the European Union and Vinova, that is a national funding agency, and most of the results that I've been showing you are under the umbrella of these different projects: Sustronic, GreenSense, Mr. TerraClean, Hyperlineum, Circle Paper, and so on and so forth. Since you will have the slides available, I understood later on.
Yes, we'll put them in the movie. Yeah,
I would like to also to just if you want to actually have it's an interesting tool. So we create a digital tour of our laboratories. So if you go on the website, you can just click on the digital tour of PIA, and it's a kind of Google map. So you can actually walk around our laboratories and see what we have available. And there are also some little snapshots on technology. And last but not least is, I apologize for the picture. It looks too serious, but that's all right. My email address is actually wrong. Sorry, it's Beni, not Beno. I will correct in the PDF. And then you have 2 links to RISE and 1 link to the Print Electronic Arena, that is our homepage. And that's it for me. I'm sorry, I probably took a little bit longer than I thought.
Thank you very much, Valerio. Very nice presentation, very educative. I think you described very well the technologies, and you gave us very nice examples at the end. And I know that you have very competitive European projects in the field. So there are already some questions in the chat.
Okay, now you ask me to see how.
Maybe again, yes.
Yeah, please, it will be easier.
Or you can also open your chat if you want.
Yeah.
Let's say Mr. Fu asks about annealing procedure.
Yes.
Actually, he describes that this curing procedure in printed electronics is challenging, and you have to be careful not to let's say, affect that much other elements. So
yeah, of course.
he
I
asked
mean,
if there is any local curing solution apart from NIR.
Local. Well, if you look into annealing, for example, metallic, there is laser. Laser is a process that could be used. If you don't have black materials, this photonic sintering is actually quite good. So you allow you to absorb the metal quite a lot of energy, so you actually can heat it up the metal quite easily without eating up too much the other materials, unless you have a black carbon or something similar that will absorb similarly the energy, and then you destroy. But yeah, it is one of the challenge, having find a good threshold between the different material. And printable piezoelectric polymers are actually a good example of this one, because they are very sensitive to temperature, so you could actually change the polarization, for example, very easily.
Okay, and these processes are compatible, I guess, with polymer substrates and.
Not all the polymers, obviously, not all the photonic sintering, yes, it is compatible. Or there is microwave sintering; it's actually compatible with PET if you work nicely. But otherwise, you need to move to things like Kapton that is can withstand much higher temperature, for example. But it's just a matter of optimization. Some of them, yes.
Okay, thank you. There's another question about. So I think the applicant asked about the scaling down of the devices. So is it possible to print on a large area and then divide to smaller pieces, or by printing we cannot reassure and homogeneous properties over the printed surface, like dicing silicon wafers after deposition?
Well, of course you can singularize them, but as I said, the scaling down is actually due to the deposition technology. So you cannot really go. There are technology that they go the order of the micron, but with the technology like screen printing, you cannot really go reliably below 100 microns, at least in our experience. What I can say in terms of reproducibility, we have demonstrated, for example, the manufacturing of on sheets of 1,000 transistors with a success rate, I think it's 95%. So you can have a very high yield as well. And the limitation it's mainly due to the technology that you use.
Okay, another question about removing surfactants and capping agents from NP used in inks without using thermal techniques that could damage the substrate. I couldn't get it very clear this. But...
Yeah, I understand. I think I understand the point. So, yeah, I'm not aware of technology that could be used in this way. I think what the applicant is referring to, of course, you need capping agent to keep particle in a very good suspensions, and usually you use thermal treatment, and then you kind of melt the particle together so that to create the conductivity. And the capping agents or pattern might actually hinder the conductivity, but I'm not aware of any technology or at least scalable technology that could be used for doing this without thermally sintering the materials.
Okay, thanks. Giovanni also asked about critical raw materials.
Yes.
And he asked about the reliability between different batches.
Batches of inks.
Yes.
Well, I mean,
to raw materials. I mean the precursors or
the raw material. Well, I mean, a lot depends of commercial raw materials. So you have you have extremely high reproducibility, extremely high quality of them. And of course, if you synthesize your own material, then it's a matter of scaling up. It's a matter of producing. I'm not, to be honest, I'm not very. I'm not very afraid about the quality of the raw materials if they are commercially available. That's not a limiting factor, I think.
Okay, I think there are many questions already in the chat, but we don't have the time. So
yeah,
maybe you can contact directly Valerio for further discussion. So thank you very much, Valerio.
You're welcome.
Okay, now
let me see if I can.
You can stop sharing your screen.
Yeah,
and then...
I will stop sharing, and I would like to say goodbye to you. I need to move on. Thank you for your time.
Thank you very much.
Bye, guys.
For your participation. Bye, Valerio.
Bye.
Okay, nice. I can see Professor Antonio Guerrero. Hi, Antonio.
Good morning. Hello.
I mean, you can share your screen without any permission. Meantime, I can just make an introduction about your webinar. So we are very happy to have with us Professor Antonio Guerrero. He will speak on the effect of contacts in halide perovskite memristor devices. A few words about Professor Guerrero. He's a professor in applied physics at the University Llamen Valencia in Spain, in Castellón. He has experience in research of more than 20 years. His background includes the synthesis of semiconductor polymers and fabrication of electronic devices. He completed a PhD in organometallic chemistry in the UK and worked for 4 years at the company Cambridge Display Technology in the UK. Then he moved back to Spain, to the University first, where he has worked in a wide range of electronic devices such as solar cells, photoelectrochemical cells, and memory devices. His main expertise is the advanced electrical characterization of devices, trying to find the link between the structure of the material and the desired function. Lately, he has been very active working in perovskite materials, and he's the author of more than 100 research articles, 1 book, 2 book chapters, and he is the inventor of 3 patents. So, Antonio, I would like to thank you for participating in the Emerge School, and the floor is yours. Thank you very much.
Okay, thank you very much, Kostas, for the invitation to this to give this presentation in the school. Okay, so as you introduced very well my talk, today I'm going to be talking about the effect of contact in halide perovskite memristors. Okay, I don't know how to remove I can see all the menu on the top, and I don't see completely my slides. But so sometimes if you feel that I'm a little bit lost, it's because of this. Okay. So just let me introduce where we are. We are at the Institute of Advanced Materials at the University Jaume I in Castellón, in Spain. So this is Europe. We are here in the north of Valencia and south of Barcelona. The INAM, the Institute of Advanced Materials, we've got more than 10 research units with more than 100 people, and we work in general in materials for energy applications. So we work a lot. We are very active in photovoltaic devices and memory devices, which is the main focus of this presentation today. But we also work on catalysis, solar cell fuel productions, and energy storage. Okay, so for today, I've divided the presentation in 2 parts. First, I'm going to be, of course, I will be introducing perovskite materials, but in the first part, I will be discussing solar cells, because the solar cells that we are working on, they are very connected to the memory devices, which is the second part of my presentation. And I will finish with some prospects for this type of devices and with some conclusions. Okay, so during these 45 minutes, my idea is to take you through some, see how we can turn photovoltaic devices using perovskites and how we can turn them into memory devices. And it's very important, the relationship between the contact and the perovskite, as I will show you. The hybrid perovskites, they have received much attention over the last 14, 15 days, mainly because they are very versatile and they are composed by some cations and anions. So the chemical formula typically is ABX3. And when we combine the monovalent cations from A, valent cations used for B, and anions with typically halide, with the right proportions to get this formulation, then we get the crystalline structure of a perovskite, which is here. So in the perovskite, we have the divalent cation in the middle of the octaedra, the halides, they are in the corners of this octaedra, and then the octaedra, they share one halide, and there's a gap here, which is filled by the monovalent A cation, which is typically quite large. So we need to combine some charge constraints and some size constraint, and when we get everything right, then we get these 3D perovskite materials with this crystalline structure. And one of the reasons why the material is very has been used a lot over the last few years is because by slightly modifying A, B, or X, we can totally modify the optical properties, like in this case, where we have the methyl ammonium lead iodide perovskite in here, and we replace the iodide by bromide, we can totally tune and modify the absorption profile. But also the electronic properties, they change dramatically when one of these cations or anions are changed. And this is well known in the literature, but this valence band and conduction bands, they will determine how easy it is to extract the charge in the solar cell. So in the solar cell configuration, which is shown here, we typically use a transparent glass electrode with a coating of FTO. For example, this is a conductive and transparent oxide, which will be the charge collector. And then we will have a active material, in this case is the perovskite, sandwiched between selective layers. I show you titanium dioxide as a selective layer for electrons, and spiron as a selective layer for holes, for positive charge. Okay, but several materials have been used in the literature, and this is not actually what I want to discuss in this presentation. But the device is finished with a metal contact on the other side, which will be the other charge collector. So basically, we have two charge collections. One is placed in the FTO, and the other one is the metal that is coated on the top. And this metal usually is made of gold or silver, or it could be carbon, conductive carbon, or other type of materials. But the device works thanks to we can illuminate the device through the transparent electrode. The light will come to active material, in this case the perovskite. We will photogenerate electrons and holes, and we need to separate them, which is quite easy to do that in perovskite. But these electrons and holes, they need to be collected in the selective layers. In this case, electrons will be collected by the TO2, and the holes, the positive charge, will be collected by the spiron and the metal on the top. Okay, so this is just to show you how spirometer looks like. This is an organic molecule, but as I said, several materials have been used in the literature. Because I don't know your background, I will explain a little bit how we characterize the solar cells. So in the solar cells, as you see here, we will have like some electrical connections that can come to a power source, or it could be connected to a potential start, so we can apply a voltage in these solar cells while we are illuminating, and then we can record the current while we sweep potential of our solar cell. In our laboratory, using tin oxide as a selective layer, we can get up to a maximum of about 20% efficiency. In our lab, we have measured devices from other labs up to 23% efficiency. And this efficiency is calculated from the maximum power point. So it's calculated from the power that can be extracted from these solar cells. So if we are applying some potential and we can extract some current, the product of voltage and current will get the power. And the maximum power is usually placed somewhere in the middle between the maximum current, which is observed at the short circuit current. So when the voltage is 0, the current that we can extract is maximum. And the open circuit conditions. So this is when the current is 0. Okay, and the maximum power point will be between the short circuit current and the open circuit potential of the devices. The current world record using this type of materials, using the perovskite, is in the range of 26% using small area devices. And the limit for single semiconductor solar cells is in around 33%. Okay, just to show you here as a comparison where we are in perovskite materials, we are very close to crystalline silicon at the moment. And if issues related to degradation of the materials are overcome in the next few years, most people believe that the perovskite materials will be the next technology to be in the market. Okay, so I'm going to show you now some slides about what people have been doing with this type of materials. I quite like this work done by the EPFL group in Switzerland, where they make this very nice matrix of materials with methyl ammonium as a cation and with formaminidium as well as a cation. And in this axis, they modify the halide from iodide to bromide. And as you can see in this matrix, the optical properties, just visually, we can all see that the device turns from dark brown, the methyl ammonium lead iodide perovskite, to quite the orange and yellow when we replace the iodide by bromide. And depending on the electronic properties and the backup of the material that is synthesized, we could maximize the current output that can be obtained from the device, and this is usually obtained for materials containing iodide because the backup is narrow, or we can maximize the open circuit potential that can be obtained in the device when we work with bromide. Okay, and of course, in the field, these formulations they have been optimized, and currently the most commonly used formulations that have a combination of cations and anions. They have mixed halides and they have mixed ions in the formulations. Okay, this is where the work where Here, there was already 4 cations in the formulations, and they were able to get 21% already in 2016. Okay. Because I'm going to speak about memory devices, it's very important to discuss about the hysteresis that is observed during the IV characterization of the device, okay? So there's one feature which is quite important for this type of materials is that when we apply this potential and we do the sweep of the potential and we measure the current, we don't get the same values of currents when we go forward, so from 0 to positive values, than when we go backwards, so from open circuit conditions to 0. And these lines, they don't overlay on the top of each other. This is called hysteresis on the IV curve. And this has been observed from the early times of the development of this technology. Okay, now I will show you one of our articles in which we modify the material selective to holes. So this is here we use a series of polymers. We use P3ST, as you see here, using the P3ST as a hole selective material. The devices, they get a massive hysteresis in the IV response. As you can see here, the separation between the forward and the backward scan is very large. But then if we replace this material here by a polymer called DPP, we totally modify the response in terms of hysteresis. And we can even suppress the hysteresis when we use the polymer PDCBT, as you see here. So when we use this type of polymer, then the hysteresis is not observed. So then we need to think about what is the difference between these polymers, and one of the main differences between them is the HOMO level of this selective complex. So the frontier energy levels of these polymers, they are very different, and the PDCBT is the one that is better aligned with the conduction band of the perovskite. And the higher the difference between the HOMO level of the whole transport layer is with the valence band of the perovskite, the larger is the hysteresis we observe. Okay, so this work is from 2018, and we have progressed a lot over the last few years to understand the hysteresis, and this is what I'm going to explain in the second part of my talk. Okay, in our lab, we get, as I mentioned, we get efficiencies of about 18% just using the methyl ammonium lead iodide, and this is our preferred formulation for fundamental studies because we don't have several ions. We only have one A cation, we only have one B cation, and we only have a halide. And then this simplifies a lot the understanding of devices. Okay, we also make quite well the formulation with the bromide, and in this case we get open circuit potentials of 1.6 volts, which are amongst the highest open circuit potentials of this type of formulation. And this is because we are getting very high quality films, and we can minimize energy losses with this type of materials. Comparing the band gap between the open circuit conditions or open circuit potential we can get with these devices, with the MAPI, with the methyl ammonium lead iodide perovskite, we only have 30%, 300 millivolts of energy losses, whilst for the bromide, we get 600 millivolts of energy losses. We believe we don't have adequate transport materials for these formulations, and this is why still these losses are quite high, and we think we could get even higher open circuit conditions this type of formulation. Okay, so let me move now to the ion migration that has been observed in the perovskite devices. Okay, we have been studying ion migration for a long time in our research group, and I've been working very closely with Professor Juan Bisquet and Professor Gemma Garcia Belmonte. We specialize in impedance spectroscopy and capacitive techniques, and also we are specialized in electrical transient techniques. And I will not go into the details of all these techniques, but they have helped us a lot to understand how the perovskite work once we apply the electrical field or once we illuminate them. And some of our input contribution to the field has been to understand these processes, provide the electrical circuits, so we can simulate and we can understand what are the limiting factors in the operation of the solar cell. So from all this information, I will show you the overall picture on how we think the solar cells based on perovskite are working. So something that is very important for this type of materials is that they are mixed electronic and ionic conductors. So this means that they are not conventional semiconductors. So once we apply an electrical field, the A cations and the X anions, they can migrate following the electrical field. And these ions, they can migrate from the bulk of the perovskite, they can go to the contacts. And we have been characterizing this migration using these electrical techniques that I mentioned. I will show you one example later. We can, for example, characterize how these ions that they come to the contacts, they generate a double layer of ions. And this is very important and because basically the perovskite is a very soft material and it behaves as if it was an electrolyte. So this double layer capacitance that we are able to observe is typical from electrochemistry. So the perovskite is behaving as if it was a liquid, meaning that the ion migration inside the perovskite is very fast. And then the ions, once they reach the contacts, they can diffuse through these Hall transport layers or electron transport layers. And in some cases, they can also give rise to chemical reactions. So here I show you one example in which we characterize the ion migration of this type of perovskite formulations. In this experiment, we place a methyl ammonium lead iodide perovskite in an interdeated electrode. So this is gold electrode, this is gold electrode, and here we have the methyl ammonium lead iodide. We characterize the material using PL confocal microscopy, and also as we are applying some voltage, we can also record the current. And if we do that, what we observe is that as the time passes, there is a dark front advancing. So the PL gets quenched, and this is because these ions, they are moving, and we are generating recombination centers. So the PL gets quenched in these recombination centers. Okay, and by developing an electrical model and understanding how fast this dark front is advancing, we can, for example, calculate the diffusion coefficient of the vacancies, the halide, or in this case, it is believed that there is a halide vacancies what is migrating inside the perovskite, and we get the diffusion coefficients, ionic diffusion coefficients very high, in the orders of 10 to the minus 8, for perovskite containing methyl ammonium lead iodide. And if we, for example, large cations that they disrupt the chemical lattice, generating like 2D domains, layer domains, in that case, the ionic diffusion is a lot lower, it's 2 orders of magnitude lower. This is one example of how we characterize the intrinsic properties of ion migration of the solar cells. But we have other techniques as well. And as I mentioned, once the ions they get to the contacts, then these ions they can also do other things like diffusing through the extraction layers, but also they can give to chemical reactions with the contacts. And this is one example that we published already in 2016. So basically, we were characterizing solar cells, inverted solar cells with the different metals. And when the device was fresh, it was giving a good IV curve. And as soon as we illuminated the devices for about 15 minutes, we could see how the devices they were degrading very fast. And this degradation given to shape curves could be partly mitigated, at least the shape of this curve could be partly mitigated if we place some protective layers between the metals and the electron transport layer. So basically, these chromium layers, they were stopping the diffusion of ions, at least partially. So the degradation or the type of chemical reactions that they could be obtained, they were stopped. And this is a clear case for reactive metals like calcium, aluminum, but also for silver. This is why most of the time we use gold, which is thought to be non-reactive, but in reality, it is also a little bit reactive, okay? So even gold, which is a noble metal, reacts with the ions coming from the perovskite. And the ions that they typically migrate are iodides in the form of vacancies. And these iodides can give to electrochemical reactions with these contacts, giving, for example, to aluminum oxides or silver iodide, and all this has been detected and reported in the literature. So these ion migrations, how the materials are migrating, is closely related to the stability of the devices. In this plot, we show how the ion migration, how fast the ions would reach the contacts, is connected to the T80. The T80 is a parameter that details the time that it takes for the solar cell to decrease the initial efficiency by 20%. And this is a good descriptor to describe the degradation of the device. So the graph is complex, so I will take you through a little bit with this. So for example, if we use perovskite formulations like using pure MAPI, methyl ammonium lead iodide, which has high diffusion coefficients, the ions they can move very fast to the contacts. The degradation when we illuminate the devices, as I showed you before, is very fast. And within the first hour, the device has degraded very, very fast. One way to increase the T80 is by reducing supply of ions that they reach the contacts. And this is obtained by, well, this is some values for mixed halide formulations, these yellow circles here. One way to reduce this ion migration is, as I showed you, to use large cations like phenylethyl ammonium or vanadium anion, which will be acting as spaces in the crystal lattice. So the ions, once they reach these spaces, they will not migrate as easily as in the case of the 3D perovskite. Okay, and depending on the proportion of this large cation, if it is 1-to-1 in respect to the lead, or if it is just combination of methyl ammonium and these large cations in different proportions, we can modify the dimensionality of these quasi-2D perovskites. Okay, the 2D perovskite would be obtained when we have only these large cations, and this mix or reduced dimensionality perovskites, they are obtained when we have a mix, a combination of this large cation and this small cation. Okay, and as you see here, when we reduce the dimensionality to the perovskite, the T8 of the device increases a lot, and then we can get up to 1,000 of hours of T80. Okay, so there's a relationship between the stability of the device and the supply of ions to the contacts. And of course, if the other way to improve the stability of the device is improving the contacts, so this is, then we have like if we take a single formulation and then we improve the formulation of the contacts, we will see like a vertical displacement for this formulation, meaning that the devices, they get more and more and more stable. And this is because the contacts, they are not reactive with the migrating ions. And there has been loads of people in the field working on this. Okay, for example, this is one example where the stability of the solar cell has been improved dramatically to more than 10,000 hours for the T80, and the illumination and using temperature. This work is by Christoph Brabeck and colleagues, and in this case by modifying the contacts. So here you see that on the top of the conductive oxide, there is 1, 2, and 3 layers, and on the top of the perovskite there is 1, 2, 3, and 4 layers, and 5 layers. So and some of the role of these layers is to stop the ions to switch the contact, which at the end will give to degradation of the devices. Okay. So let me move about lead halide perovskite. So I have introduced ion migration and hysteresis in the solar cell. So in the perovskite, as I mentioned, is the iodide in the crystalline structure, which is responsible for the main response in the hysteresis because the halide can migrate. And this will give a different type of hysteresis depending on the configuration of the solar cell. So this is the case where we call normal hysteresis. The forward gives a lower current than the backward, than the reverse. And this is what is called inverted hysteresis, is that the forward gives a higher current than the reverse scan. Okay, and if we see this very large hysteresis, then we thought, why not? Maybe we could use this type of devices to use them as a memory device. This is a memory device made by, it's a memristor made by hafnium oxide. I will explain later how a memristor works. Okay. Okay, and why we want to use these materials for memory for memory applications? And this is because to this day we are using more and more computing for everyday tasks, and we need to improve the energy efficiency of the materials that we are using. So at the moment we are using silicon for most of the tasks that we are doing, the silicon in the chips of our computers, but there are lots of different groups working in different materials to reduce the energy requirements, so we can do all these daily tasks using less energy. Here I'll show you one example where an artificial intelligence, AlphaGo, was able to beat the Lee Sedol's brain. Okay, this was at the time the best player of Go. And as you see here, the AlphaGo brain at the time, 2017, it was composed by 1,200 CPUs, 176 GPUs, 2 over 10 to the 12 operations per second. was using 170 kilowatts of energy. On the other hand, the brain of the player occupies a little bit more than 1 liter. It weighs 1.5 kilograms, is composed by 10 to the 11 neurons, 10 to the 15 synapses, and uses only 20 watts of energy. As you can see here, the difference between this artificial intelligence and the brain of the player is massive. So this is kilowatts, and this is watts. Okay. So, so this is why there are lots of groups trying to improve the efficiency of this type of computation, and there are like different issues to overcome. Okay, so this is the traditional computation where we use GPUs, CPUs, and CMOS technologies, and we have different problems like Moore's law. We have a problem as well with the memory wall, and this is that the CPU and the memory, they communicate through a bus, so there is like a problem with the transient of information between the bus. This is what is called what is memory wall. Also, because of this, computing is not efficient. The chips and the computers, they heat a lot and they need to be cooled down. So this is why different groups are trying to mimic how the human brain works, composed by neurons and working through synapses. See if we can mimic this and apply that knowledge, apply this knowledge to a configuration in which we use artificial materials that we can make in the lab in the configuration that we wish. And one of the configurations we can make, most of us, is crossbar arrays. And the idea is to have an active material that mimics how the human brain works. And here we have an electrical signal. This electrical signal comes here, and once it reaches the axon, the neurotransmitters are released, and these neurotransmitters, which are composed by ions, they will reach the next neuron. There is a transport of ions in the synapse. Then next neuron can get the signal, and then they can be transported to the next one. Okay, so the main advantages of this type of computation is that the memory is collocated, so the memory is happening around the synapse, so everything is happening here. And in principle, if we use the right materials, we could make it more efficient, so improve the energy consumption. And this, in principle, is also scalable. So how do we characterize this type of materials if we are to use memristors from perovskite? So what we want to get a device that in the IV curve that I explained for the solar cell, we want to maximize the hysteresis in the solar cells. So if we sweep voltage, we will be initially in the highly resistive state. So this highly resistive state gives a very low currents, so it's highly resistive. And at some point, the device, because we are applying this voltage and the ions are moving, the ions, they will reach the contacts, and the device will be able to extract lots of charge. And then the current will increase very fast. As you see here, this is a semi-log scale, so this y-axis is in the log scale. And then, because it's a memory, what we want it to happen is that when we go back, the device is still in this highly resistive state, in this low resistive state, in which we can get a high current. So this means that for one given voltage, for example here, 250 millivolts, we can have a state that will give low current and state will give a high current. Okay, And these devices are called memristors because this IV curve, basically what we are modifying is the resistance. So how we characterize this? So this is the same type of IV curve, but now it's linear. This is linear scale here and here. Here you see that this hysteresis is massive. So from the slope of this IV curve, we can calculate the resistance following Ohm's law. So this would be the resistance of the highly resistive state. So this is the resistance we get. And from the slope of this side of the curve, we can get the resistance of the low resistive state. Okay, so this is one way to characterize these devices. But of course, the other way to characterize this device is by using pulses. So we use pulses to set the device. So here, instead of sweeping the voltage to reach this voltage, we will apply a voltage which is above this set volts. So we can modify the device from the highly resistive state to the low resistive state. And then we also need one extra step to read the current. And this is like some examples on how we can set the device. We can read and see how the device, the current goes up when we apply these pulses, and how the current goes down when we apply pulses in the negative potential. Because these systems, because we are moving ions, the systems are reversible, and we can get back the highly resistive state by applying a pulse or going to negative potential. And of course, there are other type of more complex characterization of this type of materials, which are memristors. I will not discuss them now. I will now move on to how we can understand better these memristors coming from perovskites. Okay, so this is like a one curve, one graph in which we have all the different parameters that they are, in principle, the key performance parameters for this type of devices. Of course, we want to have high switching speeds, but those switching speeds is not bad for neuromorphic computing, because the human brain operates in the range of milliseconds. And our ions inside the perovskite, they also move in the range of milliseconds. What is very important to minimize is the switching energy. We can play with the stochasticity. It's also important to know how they integrate with the existing technologies. The retention of these states is also very important. So in principle, we want it to be highly stable over several years. And also we want to turn them on and off several times. And this is measured by the endurance. So we can do different cycles, and we want them to be as stable as possible with the number of cycles. Okay, so now I will go fast. I will just give you some examples on how we can tune this hysteresis, this IV curve I just explained to you. So this is one of our initial works in 2019. We use a perovskite with an external layer of CBM and silver contact. And at the time, we had very good response with very large on-off ratios, so between the high resistive state and the low resistive state, but we didn't understand very well the system. But now we do understand the system. We can change the system by to have only two states, which is typically used for digital computation, or we can have multiple states, which is also useful for analog computations. And we can go from here to here by modifying the composition of the perovskite, by modifying the contacts, and by modification of the buffer layers. So all this is very important. And to understand how to go from here to here, first of all, we need to understand what is the mechanism that is used by these devices to go from the highly resistive state to the low resistive state. And this review article from 2020 was clear that that nobody really knew how the system was actually activating and deactivation, and every single research group was given different reasons for activation. The main activation mechanism, which is believed at the moment, 4 years later, is connected to filamentary formation of the device. So let's say, for example, that we have a contact which can migrate, for example, silver that can migrate and can form a filament of something conductive. It could be the low resistive state, and if we can modify the position of the ions by having an electrical field, we could change from low resistive state to highly resistive state. But what we've been trying to understand over the last few years is to understand what is actually migrating inside the perovskite. Are the active metals like silver? Are the halide ions and vacancies? Is there a competition between the two different methods? This is like an overall picture of the two different situations we can have. So we could have like the halide vacancies forming filaments of halide, conductive halide vacancies, or we could have the contact forming like filaments of metal. But also we know that there can be electrochemical reactions, and these electrochemical reactions between the perovskite and the contacts can play also a significant role. So for example, if we take a device with activated ion migration, as I showed you before, like methyl ammonium lead iodide, with no buffer layer and with a contact which shows no reactivity, so that we don't have large reactivity between the gold and the perovskite, we observe this type of IV curve. And this here we only have two states, so we can do like 1,000 cycles, and the difference between the on and off, the device doesn't change very much. And then we believe that this is because we are moving the ions inside the perovskite, and we are forming these filaments of vacancies inside, and we can break the filament by reversing the polarity of the applied voltage. This type of devices, because we are moving ions inside the perovskite, gives rise to volatile response. So if the device is in the off state, we apply 0.5 volts, we turn the device on at 0.5 volts, and if we go back to the 0 volts, we get fast decay in current. So this is the initial one at 0 volts. And then we get this fast decay in voltage, and this is because the device, the response is volatile. So we recover very fast the highly resistive state when we are moving ions, just halide vacancies inside the perovskite. Okay, but when we use metal, like silver, so in this case, this is what I just showed you with gold. If we use metal like silver, then we can see the formation of a redox peak. So this could be the oxidation of silver 0 to silver 1. So here would be to get silver iodide. And then if we go back, negative potential, we get reverse reaction. We go from silver 1 to silver 0. And this type of device formulations shows that we can have these chemical reactions with the perovskite, and then depending on the scan rate, if we go very fast or very slow, the ions will form this type of filaments, and they can also show this type of memory devices. But the response is more. But this is the response. I think we are running. I will be running out of time. So
Antonio, if you can finish in maximum 5 minutes, then
yeah, when in 5 minutes you let me know, and then I'll leave it there. So these devices, because we are moving inside This is with gold, non-reactive perovskite and gold, no buffer layers. The ions move inside the perovskite, and then depending on how fast I'm doing the sweeping of voltage, the hysteresis totally changes. And this is because when we go very fast, the ions, they cannot follow the electrical field, because the electrical field sweep will be very fast, and the ions, they don't move so fast. Okay, but here we see that depending on the scan rate, it's like a set voltage in which the device begins to activate. Okay, and this set voltage, we can do a plot for different metals, like platinum, gold, which are non-reactive, which reacts a little bit. The kinetics are slow in comparison to aluminum and in comparison to silver. So we can plot this set voltage in which the current begins to increase very fast for the different metals, and we observe that there is a clear correlation between the reactivity of the metal and this set voltage. The least reactive metals like platinum or gold, we need to apply high voltages, start to see this increase in current. And this is because we need to partially oxidize the platinum and the gold, and this only happens at higher voltages. But with other metals like aluminum and copper, the materials, these materials, they react faster, and then we don't need to apply so high voltage to get the electrochemical oxidation. And in the case of silver iodide, the silver is already oxidized, it's silver 0. This is the case where we have the lowest applied voltage to get the set voltage. So meaning that silver iodide can be used as a material for low energy applications. The reason why we need to have this type of electrochemical reactions that we have here is if we are to make filaments of metal coming from the top, the metals will need to follow the electrical field. And if the metal is in oxidation state 0, not charged, and then it cannot follow the electrical field. So if we want the ions to move, the ions, they need to be oxidized. So this is why the system works so nicely when we use silver already oxidized. The silver can follow the electrical field because it's already pre-oxidized. This is how we understand the system working for this type of, when we use silver, for example, we have the background density of defects of halides. The halides, they can migrate following the electrical field. At some threshold voltage, we will induce the electrochemical reaction of silver 0 to silver 1. So we get the silver charge. And then at the voltages higher than this threshold voltage, the ions, they will follow the electrical field, making filaments, conductive filaments. And of course, because these ions are oxidized, they can go to the top or to the bottom, depending on whether the voltage is positive or is negative. So we can break these filaments, or we can form them. Okay, we can also make non-volatile response using different configurations, but I don't think I will have time to. We can also reach multiple states with different perovskite formulations and different external contacts, but I don't have time to describe that. I just want to show you as well that the buffer layer plays a very important role as well, because in the end, the ions coming from the perovskite, they need to go through these thin layers, which are typically for buffer layers in the order of nanometers. So they also can form like conductive filaments across the buffer layers. In some cases, we can even see a formation of two set features. One is coming from the halide vacancies, and the second one is the switching on through the buffer layer. And I think my time is run out, so I hope I showed you some information you didn't know about the solar cells made with perovskite, and also the connection between the ion migration of observed in the solar cells with the stability and with the hysteresis, and this hysteresis can be used to make memory devices, which in principle are low energy applications. So with that, I would like to thank for your attention, and then we have some time for questions. Thank you very much.
Thank you very much, Antonio, for this very nice presentation and overview of perovskite memristors, let's say, field. Let me check the chat for some questions from the applicants. So first is from Dr. Maria Mustafa. What could be the source of these halides and how would they enter the hybrid material matrix?
What is the source of what? Sorry?
What is the source of these halides?
The source of the halide, the perovskite is full of defects. So it has intrinsic defects. So we make our ABX3 perovskite, and because we are using solution process methods, there will always be background defect, the density of ions, and these ions they can migrate.
Yes, it's not very clear the question. Maybe the app refers to the precursors. I mean the precursors of these halides.
It's not clear where it's coming from, the halides, you mean?
Yes, the source of these halides. Maybe it refers to the precursors. I mean
okay, I will show you.
The iodide, whatever precursors.
Okay, let me show you. So basically, let me go to the relevant slide. So we have a perovskite with a ABX3 formulation. Okay, we are using, it has this type of crystalline structure, and especially because we are using solution process method, will always be defects in the material, and these defects could be like excess of lead, or it could be excess of methyl ammonium, or it could be excess of iodine, could be defect of iodine, could be defect of methyl ammonium, or it could be defect of lead, and there are other type of defects. So this has been is well known in the literature. So these ions that they are coming are basically ions that they are sharing one of these octaedra in here. There are in some places, like there are some vertices without these ions. So the ion can go from one place to one place that is missing of the halide. This can migrate from one hop from place to place until it reaches the contacts. Is it more clear now?
Yeah, I think it's okay. Another question is about so few memristors are good in forward biasing and not very good, if I'm translating well, and not good in the reverse bias.
My memristors, you mean?
Maybe the applicant refers to the hysteresis and maybe the performance of the device.
Okay.
Forward bias or reverse bias, but yes, the asymmetry between negative and positive. Yes.
Well, we have different formulations. Here I just show you some characteristic curves to understand how the system works. But we are working on improving the formulations of the perovskite and also the external contacts. So as I said, I started with methyl ammonium lead iodide because it has only one A cation, only one A B cation, and only one X anion. But then we are playing a lot with the formulations to improve the performance.
But maybe the applicant refers to the asymmetry between negative and positive. So you can see this switching for some perovskite.
No, these devices, they are not symmetric. They don't need to be symmetric because so if this is the question, it doesn't need to be symmetric because it will depend. Once the ions they go to one of the contacts, the ion has different options. One is to, when we remove the electrical field, as we do here, the ion that is here can go to the equilibrium position inside the bulk of the material. But if this ion can chemically and physically interact with the contacts, in that case, we will get a non-volatile system or partially non-volatile system, and this ion will not be released to the bulk of the perovskite so easily. So the system doesn't need to be symmetric.
Okay, thank you. I think we have only time for a very short question. One last one is about if there is any electrical equivalent circuit that you can use and simulate the memristor based on the impedance measurements.
Yeah, we've probably our last 2 years of work, we published 10-15 papers about this. Okay, I didn't want to go into that. Okay, this type of response is inductive, meaning that it shows reversible hysteresis, and the forward comes from the bottom, and the reverse comes from the top. This inductive behavior, we reported that. We can use a system made of an inductor to simulate it. It's not here, sorry. I cannot show you. But yes, we've been working on that. So just to keep it short, if the person is interested, they can contact me in my email, and then I can give this person loads of information. The email is here.
Yes, I think we are one of the best labs in the world on impedance measurements. So maybe the applicants can contact you.
Okay, this is the website. I didn't write down the email here, sorry. But you can find my email here.
Okay. So thank you very much, Antonio, again for the participation in the
for the invitation.
So now we have a break for 1 hour for the lunch break, and then we will continue with the next webinars this afternoon. So see you in 1 hour. Thank you. Bye, Antonio. Bye.
Thank you. Bye.